Hello, I am Etuate Varea, and I'll be going over the instrument suite used on the orbiter. I'll be speaking on behalf of my colleagues, Keisuke Suzuki and Varea Patel. So the orbiter's instruments are responsible for a majority of the science missions stated in the RFP. And again, these science missions are atmospheric science, atmospheric science, internal mass distribution, thermal emissions, and remote sensing of the moons and rings. To my right, you can see the 3 missions that the 8 instruments come from. Further research was done to allocate each instrument for the different science missions. Next slide. So first is the magnetometer. We'll be using the MAG. It's a heritage instrument from the messenger mission. It will be the key instrument in measuring the magnetosphere science. To my right, you can see that the MAG boom will be deployed 3 months before the Saturn flyby. And as soon as the boom is deployed, the magnetometer will be operational. Next slide. Next, we have the plasma instrument. We'll be using the swap. And the swap will also contribute to the magnetosphere science. To my right, you will see that before the second flyby, it will be checked out and the cover will be removed. And as soon as the cover is removed, it will be operational throughout transit. Next slide. So next we have the Pepsi. The Pepsi will also aid the magnetometer and the swap in gathering magnetosphere science information. It will be checked out along with the magnetometer near the Saturn flyby. This is due to the restriction that it has to be 2 AU away from the sun. Next slide. So next we have our first imaging instrument. We'll be using the NDIS. The NDIS will be used for atmospheric science and imaging in general, but it will also be a backup for the optical navigation for our GNC subsystem. The NDIS is from the messenger mission, but it will be without its narrow camera or its pivoting platform. To my right, you will see that it will be checked out and calibrated near the second flyby, and will be off during transit unless it's needed for optical navigation. Next slide. Next, we have our aerial camera. We'll be using the LORI, which is from the New Horizons mission. Now, LORI is our best camera in providing us with the best resolution, and we'll be using its capability to its fullest when we get 2 meters per pixel near the moon flybys. It will be calibrated and checked out around the second flyby, and it will be off during transit until it's needed for optical navigation.
Can you tell me what the field of view is for the camera?
Yes, the MDIS is the widest field of view because we'll be using it as the wide-angle camera.
This one right here.
Oh, Lord, sorry. I believe it's 0.15 degrees by 0.15 degrees.
Okay. Yeah.
Next slide. Next, we have the visible and the near-infrared spectrometer. For this, we'll be using the ROF, which also flew on the New Horizons. The ROF is unique in that it has 2 components, the NBIC, which is the visible component, and the LEISA, which is the near-infrared component. Now, the total data volume for the ROF is around 160 megabits. To the right, you can see that it will be checked out and calibrated around the second flyby, and will be off during transit until the NBIC is needed for optical navigation. Next slide. Next, we have the ultraviolet spectrograph. We'll be using the ALICE, which also flew in the New Horizons mission. The ALICE will be operating in the UV spectrum. And for solar occultation, we'll be using the sun to compare the composition of the rings. It will be checked out and calibrated at the second flyby, and it will be off during transit. Next slide.
I'm sorry on that one, I'm just confused. It's an ultraviolet spectrograph, but you're asking for atmospheric thermal emission. Are you using in the infrared? That doesn't make any sense.
Sure. I'll pass that question off to my colleague.
Dual range spectrometer or something?
What's the question?
Well, it says ultraviolet spectrograph, but the second bullet there says you're going to do atmospheric thermal emissions. Thermal emissions are usually in infrared. So how does an ultraviolet spectrograph do thermal emissions?
Maybe that is wrong, but
Okay, you got it. Good answer.
but on the New Horizons mission description, we did see a description about Alice telling us that it was part of the collecting data about the thermal structure of the atmosphere.
Okay.
I have a related question, I think. Did you do any analysis to show that these instruments address the science problems that are of interest at your university?
Well, all the things we've done is just research on what they've done on previous missions. And so you want to add anything?
Yeah, we haven't really gone in depth with analysis. Just basing it off of the operation.
Well, that raises an interesting question. If you take this scientists off use, the scientists are responsible for supplying the instruments, and it's not the responsibility of the project to determine whether those instruments are compatible with what is your RFP? What is your responsibility for addressing that question you just asked? Do you have any?
Not your problem.
Yeah, were you just told to use the instruments that you were given, or are you supposed to look at it and find out if we need more instruments?
Because the instruments were given as part of the RFP, the customer told us they would fulfill the RFP to the resolutions that we were told to get.
Oh.
And so it wasn't really our job to pick the instruments. It was more to use them and to use the specs that were given for them in previous missions and just integrate them into spacecraft.
So in that regard, versus operational temperatures, did you make sure you're operating in that range, -10 to +40?
Yes.
Yeah, right. That was more of what we handled with the instruments, was making sure they stayed alive.
As long as we're on the subject of temperature, do you guys have survival temperatures for these units also?
Yes, with the thermal.
We were not given survival temperatures. I think it was, from what I understood, it was difficult for you guys to find some of those things. So if you guys didn't give them to us, we only need operational. That's something we would have liked to have seen actually, because if we're only given operational, we would assume that we had to keep that operational at all times.
So that's what you did for your thermal design?
Yeah, we kept it to
Okay. That's certainly safe. Yeah. Probably over-designed, but solid. Okay.
So that was the question that I was going to ask you is, some of the instruments you're leaving on and some of them you're leaving off. Is that the criteria for which ones you leave on? Is that you needed to keep them warm?
That was based off of the functionality of these instruments. The instruments that are on are in-situ measurement devices, which means that it requires no pointing by the spacecraft. And since it's measuring the particles in space, the group that will be collecting valuable measurements while we're in transit.
But your magnetometer, for example, is on the whole time.
Correct, yes.
There's no magnetic field out there.
Oh, but it can still collect information about the particles within space.
Okay.
And this also, perhaps that won't be useful between planets and planets, but once it hits the sphere of influence of, say, Saturn, which has big radius, it'll be useful to us, and we didn't want to be sending commands every now and then so that before we hit the sphere of influence, we want the instruments to be on so that we didn't need to be sending commands by calculating the time spacecraft will hit the sphere of influence. We just wanted to have the instruments on so that we won't miss anything when we're traveling through space.
Yeah, they usually turn instruments on almost a year in advance from when they're going to be used.
Correct.
They check them out. There's plenty of time to get. Okay.
Next slide, please. So for our thermal instrument, we use the divider, which was used on the LRO mission. The divider will be responsible for detecting the thermal emissions. It will be checked out and calibrated at the second of 5 line, and will be out for the transmit. Next slide. So for the orbiter will also be performing various science. Even though it's not an instrument, it is a vital part of fulfilling the RFP mission science requirements. To my right, you can see that the radio occultation will be giving us data about the atmospheric composition, while the two-way Doppler will give us information about the internal mass distribution. Next slide.
What frequency are you using for this?
We're using the K-band.
You say there's no mass, I'm sorry, go back. No mass or power allocation, but your K-band system has to be on while you're doing these measurements.
That's true.
And you have to be transmitting to have Doppler signals.
No massive power beyond the fact that it's not already.
That's probably not available.
Well, the K-band system is on during downlink, and otherwise it's in standby, right?
Yeah.
Because you're charging batteries. So it's got to be on during this radio science phase.
Yeah, so that is actually the orbiter's highest power usage period. We are using 20 watts RF Ka band, and when we need to do dual band, we're doing KAX combined. Both of those are pumping out 20 watts RF each. And that brings us up to a total of around 70 watts or so from power.
When do you have to do, it'll come to COM, when do you have to do dual band?
Dual band during the occultations through the atmosphere.
And can you do this on the 34-meter antennas, not a rate?
That's correct. Just a single 34.
All right, so these are the different field views for the 6 output instruments. As you can see, the MBS will be our biggest, will be covering the largest area, while the LORA will be covering the smallest area. Next slide. These are different mission allocations for each instrument. And as you can see that each of the 4 scientific mission requirements are fulfilled by the 8 instruments and the radio science. So for the Aerospace science instruments, they'll be on throughout transit. We're expecting to collect about 3 gigabits of data. But there are times, like the flybys, where we will not be collecting data. And so, in reality, the amount of data that needs to be transmitted is less than 3 gigabits. And at Uranus, will be the capability of transmitting 6 gigabits. Our plan is to collect half the capacity, so we can transmit it twice to cost of 800 watts in transmission. And so next we have Christina Gonzalez, so the layout.
So all the science, all the instrumentation, it doesn't really, at the end of the day, it doesn't say like if there's a surface or where the surface is, or that's not part of this mission.
This goes over the composition of the atmosphere.
So you're running all the instruments at the same time during this whole encounter? There's a timeline for instrument usage?
There'll be some instruments on and off. Certain instruments are at the same time to be used.
So do you have a timeline?
We don't have a problem. We'll show you now. Now we'll take Christina Gonzalez, go down the layout.
Question, when you arrive at Uranus, what is the RTG output power?
What's the maximum ASRG output at end of life?
At Uranus.
Oh, at Uranus.
Yeah.
Oh, when we arrive.
Minimum.
So 135.15 times 3 plus.
It's about 400.
Sorry. So it's
406.
sorry.
131.5 times 3846.
Okay, so about 400 watts when we arrive.
Wait, after we'll get to this. After 16 years, you're getting 131 watts out of the ASRG?
No,
That's getting like.
Each?
yeah, that's beginning with like 135.85, and every single year it degrades by 1.4 watts electric.
Okay, so what do you then get when you get to Uranus?
So,
106 times 3 is 318.
I'm sorry?
106 watts.
It's got to be more like 118 or 120, right? Once you get there.
So you're about 300. Okay, so about 320 watts when we get there.
And the demand when all the science is running is what?